This is a solution to the 2013 exam paper question 5. So I'm assuming you have access to this question. So here we have a Taylor series expansion up to big O delta t squared. Okay, and the first question says define precisely what is meant by big O delta t to the n and prove this. Okay, so this is straight from bookwork, so it's kind of stuff you have to look up in the notes. So for a function, I'm going to say function if f big O delta t to the n. Okay, so big O delta t to the n is just some function. Okay, and we define big O notation as such. So f over delta t to the n. Okay, well, of course, if f, this is some function divided by delta t to the n. Okay, so this is the limit. I'm going to replace the numerator with the big O notation to the n. And what this means is this is equal to some value, okay, which is non-zero. Okay, so this means this function on the bottom is somehow larger than this function on the top. So this function on the bottom converges faster than this function on the top. Okay, so what we're going to do is prove that okay, this holds. Okay, so what we're going to do is say if f is equal to delta t squared over delta t, so I'm going to replace this f here with this. So if the limit is delta t tends to 0, big O delta t squared over delta t, all over delta t. Okay, so if I just tidy up the fraction a bit, so you have delta t squared over delta t squared. Okay, and this, of course, okay, following from this, is going to also be equal to c. So therefore, we can say that big O delta t squared over delta t is equal to big O delta t. Okay, for the second part of the question, derive the first order forward difference approximation of ut and the first order backward difference approximation of ux. Okay, so Taylor series, everything comes back to the Taylor series. Up to, okay, I'm going to do a first order expansion, so the truncation error starts at the quadratic term. So this is a forward difference, first order forward difference approximation. So this is a Taylor series. It's actually given to you on the exam paper. Now if I rearrange to make the first order derivative the subject, so I'm going to rearrange to make this term the subject. Okay, so we have the first order derivative with respect to t is equal to this term minus this term. All divided by coefficient, which is delta t. Now the truncation error, okay, is delta t squared, but I'm going to divide by delta t. Now we've seen from earlier, if we do that, you just get big O delta t, which shows that this is the first order approximation. Okay, to do the backwards approximation of the derivative with respect to x, this time I'm going to do similar, but for in terms of x, so t x minus delta x, because I'm using a backwards difference, so therefore it's t minus delta x minus delta x. Okay, so again, similar, rearrange to make this term the subject. So uxt x equals this term minus this term. Oh, actually it'll be this term minus that term. Just made a little mistake there. And that's all divided by the coefficient, which is delta x. Oh, that should be an x there. And similar with the earlier one, it's a first order approximation. Okay. Alright, next question, part B. So we have the Advection equation, by the looks of it. Of course it says the Advection equation. Spatial derivatives at the left hand and right hand boundaries are 0. Okay, at all times. Standard grid notation, we have this finite difference scheme. Show that this scheme is consistent and first order in time and second order in space. Now to do this, we replace the nodes with the Taylor series expansions. Okay, so I'll show you what I mean by that. So 5b. Okay, so this is our scheme. I'm just going to write this as given in the question. So it's forward in time and backwards in space. So what I'm going to do is I'm going to replace this with a forward difference, forward expansion, Taylor series expansion, and I'm going to replace this with a backwards Taylor series expansion in space. So u plus delta t u with respect to t, and that's order delta t squared. Okay, so that's the Taylor series expansion. Okay, first order for that term. This term doesn't need one. It's just straightforward minus u. That's all divided by delta t. Plus v. Okay, and we have u minus, and this time I'm going to use a backwards Taylor series expansion. So I'm going to have u. It would be minus delta x, but remember multiply it by minus here, so it's u plus delta x ux. Okay, and it's going to have truncation error delta x squared. That's all over delta x equals 0. Okay, so now I've got a bit of tidying up. Okay, so the u's cancel out here, and I've got a delta t times ut over delta t, so that's just going to be ut plus, okay, I've got truncation error, that's going to be divided by delta t, okay, plus v, so u's cancel out, u minus u is 0, delta x ux over delta x just gives me ux, and plus truncation error, but that's also divided by delta x. Okay, as we can see, tidy this up a bit. So that's the advection on the left hand side of the advection equation. It's first order in time and first order in space. That's showing, but it's consistent. Okay, draw the stencil for the finite difference scheme and calculate first order accurate ghost values. Okay, so the finite difference scheme. Okay, so we have UIN. Okay, so we have a node representing UIN. We have a node forward one time step. Okay, so we'll put this up here. This is UIN plus 1. And we have this node here, which is backwards in space. So that's to the left. So we have a node here, which is UI minus 1n. Okay, that's your stencil. So, oops, sorry. That's your stencil for this scheme. Okay, calculate first order accurate ghost values. Now, because it's backwards, we only need a ghost value for the left term. Okay, so if we're using zero gradient boundary conditions, and we're also going to be using a backwards difference. So zero gradient, okay, so I'm going to have u0 minus u for the ghost node all over delta x. Okay, so this u minus 1, that's a ghost node. Okay, this is my first node in the domain. Okay, this is what I want to find the value of. So if I rearrange that, quite simply, the ghost node using a first order difference approximation is equal to the first node in the domain. And final question on this exam question: using von Neumann stability analysis, stating any assumptions you make show that this finite difference scheme is stable. Right. Now, the assumptions made with the von Neumann stability analysis is that the solutions are periodic, and what this means, it enables us to replace our nodes with Fourier nodes. So therefore we can replace, I mean there's a lot more analysis that goes on in this, but sort of simply put, we can replace our nodes with single Fourier nodes. So e to the at, e to the I, k, j, x. Okay, so k is a wave number, x is your x value, t is your t value, a is some number, doesn't really matter what, because that's going to disappear, and I is the complex number. So I'm going to remember that I squared is equal to -1. Okay. Right, so what I'm going to do is I'm going to rewrite the scheme. Okay, so if I transpose everything so that our forward value in time is on the left and everything else on the right. Okay, so we have v delta t over delta x, and we have a backwards difference in space. Okay, well, if c, so what I'm going to do is let c is equal to v dt over dx, then what our scheme is equal to uin minus c uin minus ui minus 1n. Okay, I could simplify this a bit more by actually saying 1 minus c uin. Okay, so I've got 1 there and I've got a minus c lot there of uin, and that's going to be plus c times ui minus 1n. Okay, so minus minus gives us plus. Okay, this enables, writing it in this form makes things a lot easier for this particular analysis. Okay, so what I could do is I'm going to replace each of these u's with the Fourier nodes. So we have e to the a t plus delta t, okay, because n plus 1 means t plus delta t, I, k, j, x. Okay, a lot of this is going to simplify at the next stage. Okay, so uin is e to the at I, k, x, and that's multiplied by 1 minus c, plus, and then I have e to the at, e to the I, k, j, and now I minus 1 means we have x minus delta x, and that's times by c. Okay, well, if I divide everything by this term, these two terms, what I get is e to the a delta t on the left. I get 1 minus c plus e to the minus I, k, j delta x. Okay, so that's from here, times c. Okay. Now what we have is the stability. We need this. This is like a growth in the error. Okay, e to the a could be any number, but e to the delta t, we need this growth in the error to be less than 1 for stability. If it's greater than 1, the error just keeps compounding and we have an unstable scheme. So for stability, we want the magnitude of e to the at to be less than or equal to 1. Okay, so in other words, we want the magnitude of 1 minus c plus e to the minus I, k, j delta x c. So that's what we want. Okay, for what values of c is this satisfied? Now, what I can do on this one is use the triangle inequality. Okay, so I'm going to have 1 minus c, okay, plus e to the minus I k j delta xc. So this is using triangle inequality, which means the magnitude of a sum is always less than or equal to the sum of a magnitude. Okay, so this right hand side is going to be greater than this value here. Okay, now what we can borrow a result from complex number theory, and that the magnitude of e raised to the power I times anything, okay, that will just becomes 1. Okay, so what this means is we have 1 minus c plus c. Okay, and that is equal, 1 minus c plus c is equal to 1. Okay, so this means, so therefore the finite difference scheme is stable for values of c in the range 0 to 1. Actually, it's not equal to 1. Okay, so if c was 2, okay, we'll have 1 minus 2, or let's say c was 3, sorry, we'd have 1 minus 3, which would be minus 2, because it's absolute value, that becomes plus 2, plus 3, so that's not less than or equal to 1. So the only time this is satisfied is when c is between 0 and 1, so hence when it's stable. Okay, and that's the question 5 complete.